Now, as a prelude to the modified and improved divide and conquer algorithm, here's a slight digression. It's not really a digression, but it's a simple problem which will help us come up with an idea that we will be employing in the modified algorithm. So suppose you're given this simple task of calculating the product of two complex numbers, a plus bi and c plus di. A straightforward way of multiplying these two complex numbers would be to multiply them term by term. So a multiplied by c would be ac, bi multiplied by di would be minus bd, because I square is minus 1. So this is the real part of the product. The other two terms will make up the imaginary part of the product. A multiplied by di would be ADI, and BI multiplied by C would be BCI. So if we take I common, the imaginary part of the product is BC plus AD. So this is the product of two arbitrary complex numbers, A plus BI and C plus DI. Now notice that if we actually want to compute this product, we would need to do 4 multiplications. We would need to multiply A with C, we would need to multiply B with D, we would need to multiply B with C and A with D. And of course we would need to do an addition over here and a subtraction over here. This one is not really an addition because we have to generate the real part and the imaginary part separately. So there won't be any actual addition corresponding to this plus sign. Now assuming that multiplication is a lot more expensive than addition and subtraction, if we want to improve the amount of time it takes for us to calculate the product, it would be great to cut down on the number of multiplications, if there is a way to cut them down. So here we have 4 multiplications necessary to compute the product. Here's a better way to compute the product, which will require one less multiplication. Let's say we take a plus b and multiply it with the number c plus d. What would be the result here? The result here would be a times c plus b times c plus a times d plus b times d. Now, one way to calculate this imaginary part, bc plus ad, is to calculate this product b times c and to calculate the product a times d and then to add them together. But suppose we do this one multiplication, a plus b times c plus d, and suppose we calculate what a times c is and b times d is. So let's say we do these 3 multiplications. We can generate bc plus ad directly, because if bc plus ad is if bc plus ad can be written as a plus b times c plus d minus ac minus bd, and if we have already calculated these 3 terms via 3 multiplications, we won't need to do an extra multiplication to compute bc plus ad. We can directly calculate what it will be by taking the first product, subtracting the second product from it, and then subtracting the third product from it. So using just 3 multiplications, we can compute what bc plus ad is. We don't need 4 multiplications. We don't need to actually compute each of these 4 terms separately. We can optimize this calculation by computing a plus b times c plus d. Of course, we would need to do these 2 additions first before we can multiply them. But then we are trying to cut down on the number of multiplication operations, assuming that addition is cheap compared to multiplication. So let's use this same idea to modify our divide and conquer algorithm to modify our divide and conquer algorithm and hopefully end up with a more efficient algorithm. Recall that the product of A and B is given by this expression. And in this expression, we had to make 4 recursive calls to subproblems of half the size, where we have to multiply two n by 2 bit numbers together. So there are 4 such multiplication operations that we need to do. Let's use the same idea that we just saw, which I called as a digression, but we're going to use pretty much a very similar optimization to cut down on the number of multiplication operations and therefore the number of recursive calls. So here's what we'll do. We'll compute AL plus AR multiplied with BL plus BR separately this is a single multiplication operation. Okay, this is one multiplication, and of course the number of uh, addition operations may slightly go up here. We have 2 additions here, and if we open this up term by term, we'll get AL multiplied by BL plus AL multiplied with BR plus AR multiplied with BL and AR multiplied with BR. Now if we go back and see what 3 terms we need, we can compute AL times BL and AR times BR using 2 multiplications. So we have one multiplication operation here, one multiplication operation here. And assuming that we have computed this product using one multiplication, notice that we can directly get the value of AL times BR plus AR times BL, which is this, by taking this result and subtracting AL times BL and AR times BR from it. Right? So this expression is equal to this result minus ALBL minus ARBR. And using 3 multiplication operations, we could compute this value. In other words, we could compute this value by 3 multiplication operations. One for computing this, one for computing this, and the third one for computing this. And we can generate this product or this expression, this sum, by taking this result and subtracting these 2 terms from it. Now, this would take one recursive call, this would take another recursive call, and this would require another recursive call. So there would be 3 recursive calls required in this modified algorithm instead of 4. Let's look at what the algorithm is. Let's look at the pseudocode. So we want to multiply these 2 numbers A and B, which have a length of n. If any of them have a length of, let's say one of them has a length of n and the other one has a length less than n, we can always pad the shorter number by zeros on the left. So for simplicity, we'll assume that both these numbers have a length of exactly n. Now if n is equal to 1, or if n is small enough, say less than 16 or less than 32 or whatever the upper limit of the integer data type is in the programming language you're using, we could directly compute A times B by using the inbuilt multiplication operation, which runs in a constant amount of time. So if we come here, we are assuming that n is not small enough, n is pretty large, and so we need to divide this overall problem into subproblems. So we'll take out the first n by 2 bits of A and assign the resulting number to A sub L. We'll extract the right half of A, interpret that as a number and assign it to A sub R. Then we'll take the left half of B, assign it to B sub L, and the right half of B is what we'll assign to B sub R. Then we'll compute these three products, P1, P2 and P3. And these are the three products that we saw over here. P1 is A sub L multiplied with B sub L. This is the product that we are calling as P1. P2 is the product of A sub R with B sub R. So this is P2 and this is going to be P3. Now these products are products of two n by 2 bit integers, which is why the third parameter here is n by 2. We are making a recursive call on these smaller integers whose length in terms of number of bits is half that of the original two numbers A and B. So these are smaller subproblems. Notice that AL plus AR and BL plus BR are also approximately n by 2 bits, because if each of them is individually an n by 2 bit number, then their sum will also be approximately an n by 2 bit number. One could argue that it could be n by 2 plus 1, but then, you know, if you work out the math, it's not going to affect the asymptotic complexity even if we add a plus 1 over here. So let's assume here that these are all products of n by 2 bit integers. Now, in order to compute and return this product of A and B, we need to combine these three products P1, P2 and P3 into the overall result. So we'll take P1, we'll multiply it with 2 to the power n. This is P1, this is P2, this is P3. So we'll take P1, multiply it with 2 to the power n, or equivalently shift the number to the left by n bits, or append n zeros to the right of this number P1. Take P2 as it is, take P3 and append n by 2 zeros to the right of it, and then add these three numbers. So what would be the length of, so firstly this shifting operation, or this operation of appending zeros, is going to take time proportional to n, because we are appending n zeros here and n by 2 zeros over here. So that's going to take time proportional to n. What about the time for adding these three numbers? What would be the length of AR times BR? The length of AR times BR would be approximately n. If these are n by 2 bit integers, their product could have a length of approximately n. These two have individually an approximate length of n bits. Their sum will have an approximate length of n bits, or maybe n plus 1, it doesn't matter. If we add n by 2 more bits to it, because we'll be adding n by 2 zeros over there, the length of this result would be approximately n by 2 zeros plus the length of this sum, which would be approximately n. So this would be about 3n by 2 bits. Now this would be about n bits, and then we are adding n zeros here, so this would be about approximately 2n bits. So we are taking a 2n bit number, adding it to a number that has 3n by 2 bits, and adding the result to a number that is n bits. So this is going to take time proportional to n. So we can write the last line here as return P1 multiplied by 2 to the power n plus P3 minus P1 minus P2 multiplied by 2 to the power n by 2. So actually we won't be computing this directly, we'll be computing this by using our optimization, which is to take P3 and subtract P1 and P2 from it. So there'll be two subtraction operations here, but again, since the lengths of P3, P1 and P2 are proportional to n. The time taken for this will be proportional to n. Time taken for calculating this will be proportional to n, and the time taken for calculating this, of course, the time taken to calculate P1 and P2 will be T of n by 2 each, but the time taken to shift this result to the left by n bits, or time taken to append n zeros to the right, will be proportional to n. This shift operation will also take time proportional to n. These two subtraction operations will take time proportional to n. And finally, these two additions will take time proportional to n, as we just saw, because the lengths of the three numbers that we'll be adding are given by these expressions, which are proportional to n. So we can write the recurrence for the running time for this modified algorithm as T of n is 3 times T of n by 2, because we have 3 multiplication operations now instead of 4. So we have 3 recursive calls to this same function multiply, and then the rest of the lines which basically are dividing the problem into these subproblems and then combining the results of these subproblems into a solution to the original problem. That particular work is taking time proportional to n, because every other step over here is taking time that is proportional to n, and there are a constant number of such steps. So the overall time will be some constant multiple of n for combining and dividing the problem. For combining the results and originally dividing the problem into the subproblems. Now this is again a recurrence that we can solve using master theorem. A here is 3, B here is 2, and f of n is this linear function of n, c times n. So if we compute n to the power log base b of a, we'll get n to the power log base 2 of 3, which is about approximately n to the power 1.59 or maybe 585 to be more precise. Now this function is polynomially larger than f of n. So again we are in case 1 of master theorem. By case 1 of master theorem, we can say that the time complexity T of n will be given by theta of n to the power log base 3 of 2, or n to the power 1.59 approximately. Now this is better than the two algorithms that we've seen. It's better than the brute force paper and pencil algorithm, which took time theta of n square, and it's better than the divide and conquer algorithm that we saw in the previous video, which was based on a straightforward approach of making 4 recursive calls instead of 3. So it's better than both those algorithms, but this is also a divide and conquer based algorithm. So you could have different divide and conquer algorithms, each with different asymptotic time complexities. So again, divide and conquer strategy does not guarantee that you will that the efficiency of the resulting algorithm will be the best possible efficiency for that problem, and there's no guarantee that different divide and conquer algorithms will yield the same time complexity. It depends on how you optimize the algorithm. In this case, we used this simple strategy of minimizing the number of multiplications, which translated to minimizing the number of recursive calls, or reducing this value of a from 4 down to 3, which had a role to play in the reduction in the time complexity of the algorithm to theta of n to the power 1.59.